In the second lecture, we will be talking about subsurface exploration. So we have two objectives for this lecture. The first objective, you will need to be able to tell the purpose, components, and the typical procedure of subsurface exploration. Second, you need to be able to describe boring, SPT, CPT, and vein shear tests. Actually, you need to know both the equipment and measurements. Actually, I put two other things here. One's called DMT and PMT, but for both of them, I place an asterisk on them. The purpose is to let you guys know that I can provide the information in case you need, but it will not be required in this course. So first, let's take a look at the purpose of doing the subsurface exploration. To understand the purpose, I want to remind you guys of the name of this course. Again, what's the name of the course? It's Foundation Design. So apparently, after taking the course, we need to know how to design a foundation. So design is the ultimate goal. But for designing a foundation, we need to know a few things. That is the input of the design. So what do we need to know? One thing is the loading. So we need to know how much load we need to sustain. And that usually comes from the structural engineers. And the other part, which is the major content of this course as the input of design, that's the material properties. And we need to know the material properties of the soil for foundation design. Actually, there's some reasons. The first reason is that soils is not like what we have in structures like concrete and steel. For concrete, as long as you know the number, so for example, C30, you know the strength of it. But for soil, that's not the case. So usually the property is unknown. More than that, in soil, we have very high variability. That is, if we move from one side to another side, we will expect high changes in the soil properties. And even at the same site, you move from spot to spot, the variations in the material properties can also be considerable. So in order to get the material properties, usually we can get such information from something called a soil report or a Geotech report. And in order to get that Geotech report, we need to conduct the soil or Geotech investigation. Second, let's take a look at different components of the Geotech investigation and how that will be related to subsurface exploration. And for Geotech investigation, we have three categories of tasks. The first category is called site investigation. The purpose of conducting site investigations is to obtain the soil profile and samples. The second category of work is lab testing. And to do that, we usually just collect some samples at the site and then bring the sample back to our lab where we have the testing equipment. And we run the lab tests and obtain the material properties for design. Third category of work is in situ testing. For this one, instead of bringing samples back to the lab and run the tests in the lab, we can bring the testing equipment to the field and test the samples in the field directly and get the properties right away. So for this one, we test in situ samples for properties. Then let's take a look at site investigation. For site investigation, we also have different categories of work. Usually the first step for site investigation is to collect information, especially the background information. So the first, info and background investigation. And this step can be done without going to the field. Usually we can try to find out what type of foundation we're gonna build, and what about the loading, and what code we can refer to. Also the history of the sites, hydrology, about the water conditions. And the second step is called the field reconnaissance. And for this one, in order to get a more in-depth understanding of the field and identify information that we cannot find in the existing reports, we need to go to the field and we observe things such as water, waste. The last step or category is called subsurface exploration. And this is the one of interest into this lecture. For subsurface exploration, we also have three components. The first one is boring. So when we say boring, basically we drill a hole into the ground. Second, sampling. So we collect samples. And sometimes boring and sampling can be conducted simultaneously. The last one is testing. And the cool thing about subsurface exploration is that testing can also be conducted as we conducting boring and sampling. Then let's take a look at boring, sampling, and testing one by one. First, boring. The purpose of boring is to obtain boring log. And we have different types of equipment that we can use for conducting boring. And the most common one is the auger. And two common types of auger. One is the hollow auger. So we have a hollow stem for this type of auger. Because this hollow auger is open-ended, so we can use it to collect samples. The second is a solid stem auger. And a more advanced type of auger, which has been used a lot of these days, is called a continuous flight auger, CFA. And we will be talking about this again in later lectures for deep foundations. So So we also have something like, the rotary wash boring. So we can add a liquid like water or fluoride as we are conducting the boring to facilitate the rotation and the drilling of the drilling equipment. For boring, we need to know a few extra things. That is, for example, when we conduct the boring, the first question after we know what type of boring equipment we're going to use is, where are we going to do the boring and how many bore holes that we will need, how deep we need to go. So here I'll give out a few examples. First one, this is for the equipment. I will give out a few typical examples. For example, we have something called the International Building Code, IBC. IBC defines that for buildings with areas that's over 2,500 square feet, we need to have one borehole. For bridges, we have ASHTO design guidelines. That's for bridge. And for this one, for any substructure, that is a pier or an abutment that is less than 30 meters wide, we will have one borehole. That's how many boreholes we need to have. So that's for spacing. And for depth, one rule of thumb that we can use is this equation. D, here's the depth, equals 10 times S to the power of 0.7. So here S is the number of story. This is for boring. Next, sampling. So for sampling, one of the first things that we need to know about is something called disturbed sampling and undisturbed sampling. And from name, we can see that undisturbed sampling means the soil sample that we collect has very similar structure to that in the field. And disturbed sampling will cause considerable changes to the structures of the soil. And for possibly most of the tests that you conducted in your soil mechanics labs, you use disturbed soil samples. And the disturbed soil samples can be used to obtain soil properties such as unit weight, water content, particle size distribution, PSD, Atterberg limits, organic content, and compaction. And these soil properties, they do not change too much as we alter the structure of the soil. But for some other soil properties, we need to use undisturbed samples. Such as strength, consolidation, and for these soil properties, sometimes if we run the tests on both the disturbed soil sample and undisturbed sample of the same soil, and you can find that the measured values will be much different from each other. And in the field, we have undisturbed soil sample. So that's why we want to conduct undisturbed sampling to get undisturbed samples, so that the soil properties that we measure with these samples will be close to the true value in the field. We have two types of equipment for disturbed sampling and undisturbed sampling. And for disturbed sampling, we usually use the split spoon sampler. So the sampler is a cylinder consisting of two pieces. And for the cylinder, the outer diameter is 50.8 millimeter, or 2 inches, and inner diameter is 34.93 millimeter, or 1 3/8 inches. And for undisturbed sampling, usually we use the thin wad tube. For the thin wad tube, the outer diameter is also 50.8 millimeter, so that is 2 inches. And inner diameter is 47.63 millimeter, or it's actually 1 7/8, so 1.875 inches. If we compare the outer and inner diameters of the two types of soil sampling equipment, we can see that the undisturbed, this thin wad tube, has a greater inner diameter than that of the split spoon sampler. So that means the wad's much thinner. That's why many people also call the split spoon sampler thick wad sampler. And if you want a criteria for differentiating equipment for undisturbed soil sampling from that for disturbed soil sampling, we can use the definition of area ratio. So here we use A. A is the ratio between D0 squared minus DI squared, then the quantity divided by DI squared. And if we try that for both of them, and the A for the split spoon sampler will be 111%, and A for the thin wad tube is about 13%. Actually, the criteria is that if A is less than 10%, so that is undisturbed. And it's greater than 10%, is disturbed. In this case, 13% is higher than 10%, but they're very close. So usually we still believe that the thin wad tube is undisturbed soil sampling equipment. Then let's take a look at a different testing that we have for subsurface exploration. Let's start with SPT. SPT is short for standard penetration test. And if you want an official description of it, you can go to ASTM D1586. and it was developed in 1958. So the SPT test uses a thick wad sample tube with an outside diameter of what we just mentioned, 2 inches, and an inside diameter of 35 millimeters, and a length of 660 millimeters. And we drive the sample tube into the ground at the bottom of the borehole by blows from a slide hammer with a mass of 140 pounds, falling through a distance of 30 inches. The sample tube is driven 150 millimeters into the ground, that's 6 inches. And then we count the number of blows that is needed for driving the sampler by that distance. And typically we repeat that blowing process every 5 to 10 feet. So after we've counted the blows 6 inches for one depth, we will drill to another depth that's 5 to 10 feet away. So if we summarize the procedure, usually we drill to the depth of interest, and second, we use a split spoon sampler. Few numbers to remember. That is the mass of the hammer, so 140 pounds. And the distance of falling is 30 inches. And the third step, that's the key. We want to record the number of blows. So usually we drill 6 inches. So that's 18 inches in total. And we only record the blow number for the last 6 inches, and record the ends. We call it the end number. After step 3, we drill to another depth, which is usually 5 to 10 feet away. That's deeper. And repeat step 1 to 3. And for SPT, possibly many of you will not conduct the test yourself. But even you don't do it, you need to understand the results that we will get from the SPT test. We need to interpret the results and know how to use the results for our design. Actually, in many of the following lectures, the SPT results will be correlated with some other soil properties that we will use for our design. And for the SPT results, we know that the number of blows that we record is the N number. And you can see that we already defined the mass of the hammer and the falling distance so that we can standardize this procedure. So everybody in the world, they can get the same numbers going through the same procedure. Despite the efforts that we have made for standardizing the SPT, we will find that we have different equipment, and even the same equipment, as we move from one side to another side, we will also have some changes in the machinery. And one thing that can change a lot, that's the hammer efficiency. So to standardize we want to define that everybody will use the same hammer efficiency for getting the N numbers. And that efficiency is 60. So we need to convert n number to n60. And for doing that, we use the following equation. N60 equals a fraction times the raw n number. And for the fraction, numerator, we have EM. That's the energy efficiency. I will explain more. We have C sub B, C sub S, and C sub R. And numerator, we have a constant, 0.6. E sub M, energy efficiency, is defined as the ratio between the energy that we apply to the hammer and the total applied energy. So there's a difference between these two because we're gonna lose a lot of energy, due to friction and some other factors. And total applied energy usually can be obtained as the product of weight times the falling distance. So this EM is energy efficiency. The other things, C sub B is relevant to the condition of the borehole. C sub S, here the S stands for sampler. So we use different samplers. We're going to get different numbers of C sub S for this correction. C sub R is for rod length. So that's the first step of the standardization. Second step, we will move from N60 to N160. And here this correction or standardization step was conducted for stresses. The reason is that, even we get the same number, but in a different depth, they may mean total different things. As if we move from one soil depth to another soil depth, we can expect that we will have different confining pressures. The deeper that we go, the higher the confining pressures that we have. And more compressions we have, that will change the meaning of the N60 number. So in order to make sure that the N60 numbers tell the same soil property, we add this 1 here to represent the confining press. And here 1 means a confining stress of 1 atmosphere. So could you guys tell me what's the value of 1 atmosphere? Any of you still remember? Okay, I'll give you the values. Actually 100 kilopascal. Or we are talking about the US customary units. That is 14.5 psi. Just keep in mind, we will use this value a lot in later lectures. So N160 equals N60 times the square root of P sub A over sigma Z 0 prime. P sub A is 1 atmosphere. And sigma Z 0 prime, that's the confining stress along the Z direction. So again, in soil mechanics, as I mentioned, with Z means vertical and X means horizontal. And here 0, that means initial. And the prime means effective. So you can see that we will see 1, 2, 3. Prime means effective. And sigma is stress. So in order to do that, as long as you know the location or the depth of a point in the soil, we can use what we learned for calculating the stresses in the ground before they calculate this sigma z0 prime. So this is for SPT. So I want to show you guys one video so you can take a look what a SPT test looks like. You can see that actually we cannot see the hammer, but it's coming down from the top and drill the rod into the ground. So in that process, we need to count the number of blows as we drill the rod into the ground by 6 inches. So we can go pretty deep. And in order to do that, we need to add the extension rod as we continue the drilling process. So this guy is showing us the split spoon sampler, and it has 2 pieces. If we disassemble it, we can see the soil sample. So this is what a SPT test looks like. The next type of test is a CPT. And a CPT is short for comb penetration test. CPT has a total different philosophy than SPT. For SPT, we count the numbers to drill the sampler by 6 inches, but CPT, we measure the resistance force that we get as we drill the comb into the soil. So this test consists of pushing a instrumented comb with the tip facing down into the ground, usually at a controlled rate. That's passed somewhere between 1.5 and 2.5 centimeter per second. Tip of the comb looks like this. The apex angle is usually 60 degrees, but we have different variations of CPT, and for those variations, we may have different apex angles. And the rod, we also have different dimensions, but the most common ones, one has a dimension of 3.5 centimeter. So that corresponds to an area of 10 centimeters. We also have D equals 4.2 centimeter. That's another type of comb. And that corresponds to a sectional area of 15 square centimeter. And for the CPT, instead of getting a count number, we need to get the resistance. And there are 2 types of resistance that we need to get. So you can picture this. If you want to insert a rod into the ground and with the apex angle like this, so what will the resistance come from? Think about this. It's not difficult to figure out that one source of the resistance will come from the tip, right? And what about the other one? Friction on the side. So for CPT, we need to get two things. One is called Q sub C. Q sub C is called the comb resistance. And the comb resistance equals the total force, the total resisting force that we will get, divided by the projected area. So that's actually the sectional area of the comb. So it has a unit of pressure. Or PSI. And in this course, usually we reserve Q, F, and P for stress and forces. And if it's a small letter, like a small letter Q, that means it's the pressure. If we use a capital letter Q, that usually means it's the force. So the comb resistance tells the total resistance. And in order to tell side resistance, well, here we use the term sleeve friction. Sleeve actually is the side surface of the comb. And the sleeve friction equals the total frictional force. So that is part of the total force. The other part is the tip force, tip resistance force. Divided by the sleeve surface area. And in many cases, we can see another term. It's called a friction ratio. R sub F, which quantifies the comparison between the sleeve friction and the comb resistance. So it's the ratio between F sub S and Q sub C times 100%. And for CPT, I want to mention a few things. These days, it's the common that people add different sensors into the CPT to provide more function. For example, we can add pour water pressure sensor. In that way, we will get something called CPTU, and the U here stands for water pressure. We can also add seismic sensors. So that's a dynamic sensor, so that we can get dynamic soil properties, such as shear wave, velocity. I wanted to point out that these days, the majority of the CPTs that you will possibly see, they are electronic ones. In the old days, you will possibly still see, the dial gauge, which they have a steel rim, and you can read the force that you get. But the modern CPTs, you can get the reading, with some type of data logger directly, or embedded data logger of the CPT. So let's take a look at another video for CPT. You can see that through this process. shows the variation of Q sub C and F sub S with the depth as we drill the core into the ground. The equipment that is shown in this video show you the base. All the data recording down automatically, and we can even see real-time graph for variation of the Q sub C resistance and slip friction. And the last type of subsurface exploration testing equipment that we need to know about is the vein shear test. So this one is more common, and we use a handheld device for which the cost is usually low. So it's very common to see this one. For this one, we have a shaft, and we have 4 veins. And if we take a look at the cross section, it's going to be look like this. This is the shaft. This is the actual cross section. This is the side view. We also have some vein shear test device. The vein could be tapered. For the vein, we have 2 geometry parameters. One is D. The other one is the height H. And usually height H equals twice of D. So when using the vein shear test device in the field, we also need to define how fast we're going to rotate the shaft. So what's going to happen is that we will insert the shaft into the ground to the depth of interest, then rotate it at a rate of about 0.1 degree per second. So you can see that even we rotate it at this rate, it's still pretty fast. So there's no time for the water to escape. There's no drainage. So the soil property that we will get is going to be undrained. And for drainage, even we're talking about sand, the drainage will take minutes. And for clay, we know that they can take decades or even centuries. And the soil property that we get, the strength, is a C sub U. So we will get the undrained shear strength as the result of vein shear test. And to get C sub U, we measure the torque at failure. As T. So we rotate the shaft at this rate until the vein will create a sliding surface in the soil. And T is the maximum torque in that process. So let's take a look what a vein shear test looks like.
The hand shear vane is a small portable device for measuring the undrained shear strength of cohesive soils. Tests may be undertaken in situ or on intact samples of material. Avoid disturbed material, as this will give misleading results. Our vanes are calibrated each year. Check that a valid certificate is provided with the vane. Remove the cover. Check for bent rods and a clear mechanism. Do not use the instrument if damaged. Attach the required vane spindle using the spanners provided. The larger 33mm vein is suitable for soils of very soft to soft consistency. If using, then read the inner scale on the dial. The smaller 19mm vein is suitable for soils of soft to stiff consistency. Read the outer scale on the dial. Rotate pointer clockwise to rest on the dog plate. Insert the vein perpendicular to the soil without side movement to a depth of 70 to 80mm in situ or to the centre of the sample. Avoid stones and other obstructions. Record refusal if too stiff to insert and note any anomalies during the test. Turn the dial clockwise at a speed of 1 revolution per minute. You could follow the second hand on a watch. Rotate as slowly as possible whilst maintaining a stable movement until shear occurs. The pointer will stop moving. Record the peak shear strength in kilopascals, kPa, to the nearest single digit. Measure residual or remolded strength by rotating the vein rapidly through 2 revolutions. Immediately reset the test pointer and rotate again slowly within the same position. Carry out 3 tests in separate locations in a trial pit or at about 100mm intervals in a core sample within the same stratum if possible. Avoid any areas which are likely to have been disturbed. Report the test depth, all readings, and the hand shear vein reference number. When complete, dismantle the instrument using the 2 spanners provided. Wipe clean with a damp cloth and put back in the box ready for next use.
You can see that it's a pretty simple test. And after getting the torque T, that's the maximum torque in that shearing process, we can calculate the C sub U undrained shear strength using a very simple equation. So T C sub U equals T torque divided by K, which is the geometry factor and the lambda. So we can have different geometries for different vent shear test device. For example, for very common rectangular vents, K equals 7 times pi times d, that is the diameter, squared divided by 6. And lambda here is a correction factor and this factor is proposed because people found that the measured values are usually too high. And we have different correlation equations to calculate lambda based on some other soil properties. For example, here I'm giving out a very simple one. Lambda can be related to Pi, the plasticity index, using this equation, 1.7 minus 0.54 times the log of Pi. This is what we need to know about subsurface exploration. Again, the reason that we want to learn these things is that in the following lectures for foundation design, we need input, especially material properties. And for material properties, for many of them, we will try to get the material properties values based on the results that we get from this CPT, SPT, and vent shear tests. So we can, for example, we get an N number, and using some correlation equations, we can calculate the properties that we need, such as the unit weight. So next, let's take a look how to connect the subsurface testing results to the material properties that we're gonna use in our design. So for this purpose, researchers, they have developed a lot of correlations between the testing results. Actually, they are not real soil properties such as n number. It's just an index. So we have the correlation between indices. Their numbers quantify the soil properties, but they do not have physical meanings. And soil properties. Soil properties are also numbers, but they have physical meanings. So for these correlations, I want you guys to think about what type of soil properties do you think we will need for our design. And to get an answer, you can think about what we learned in soil mechanics. So first, we talked about the weight volume properties, right? The soil index properties and soil consistency. So the first category is the index properties and the soil consistency. And for this one, two most common ones. One is gamma for unit weight. And the other one is D sub R. And we will use D sub R a lot in our design. But it's for sand only. So that's the relative density. And after talking about basic property of soil, then we move to the water issues. But in foundation design, the consideration of the serviceability of foundation with respect to drainage issues, they're secondary. So we will not discuss that. And after water movement, we move to stress. So when we are learning soil mechanics. And for soil properties relevant to stresses, the most common one is the K sub 0. So that is the coefficient of lateral earth pressure. We need this one to relate the stress along the vertical direction to the stress along the horizontal direction. This is because for the stress along the vertical direction, sigma z, we can calculate it based on the depth and the unit weight of the soil above that point of interest. But for the stress along the horizontal direction, there's no way that we can directly calculate it. We usually assume that the ratio between the vertical stress and the horizontal stress is a constant. That is K sub 0, and it's the soil property. Then after we know how to discuss stress, we start talking about sediment. That's displacement, deformation of the soil. For sediment, we need to know the Young's modulus and Poisson's ratio. Also, for consolidation, we need to know the over-consolidation ratio, OCR, and sigma C prime. This is pre-consolidation stress. This high is the stress that the soil point experienced in its stress history. So after we know how to talk about the deformation of the soil, last, we need to talk about failure. So that is the soil strength. For soil strength, we have things such as C sub U, that's the undrained shear strength. Or sometimes we C sub prime, that's the effective cohesion, and also phi prime, that's the effective internal friction angle. So C and phi, they are used in the Moore-Coulomb model for defining the soil strength. make sure that you still remember these basic things. If you don't, take a look at your notes in the textbook for soil mechanics to quickly go through the content. Here again, prime stands for effective. That's what we are talking about, effective stress. So C prime and phi prime were obtained if we use effective stresses. If we use the total stresses in the total stress design, we will get C and phi instead of C prime and phi prime. And for the correlations between the indices, that's the measurements that we obtain in the subsurface exploration testing, and the soil properties that we will need for designing foundations. We have a lot of them. Actually, people are still working on these correlations and continue to propose new correlations to better predict these soil properties for design based on the indices. If you take a look at your textbook on page 97 to 128, you will see a lot of equations. We will have one lab to practice how to calculate soil properties with the subsurface testing results, that is the indices, based on some selections that we can find on the textbook.
I think I'm falling for you.